All right, so welcome to this series of beam analysis. So in the previous videos, we looked at introductory concepts that we need to know in order to solve problems. But now we're going to look at solving problems, okay? So in this first example, we have an example of a cantilever beam. So cantilever beams are fixed at one end and they don't have any other support, so it's just a hanging beam, right? So we have a cantilever beam, and what we need to do is we need to solve reactions, and then we need to draw our shear and moment diagram. First thing that we need to do is we need to solve our reactions. So let's say this is point A and we have our three reactions. We have a reaction in the Y direction, we have a reaction in the X, and we have a reaction as a moment, right, around this point. First thing that we need to do is we need to write our equilibrium equations. So if you remember from a previous video, this is a determinate beam. So this beam is determinate. It has three reactions and one member. So if we had one more, say we had a roll or support here, we'd have one more reaction, and then this beam becomes indeterminate. Because we have a determinate beam, we can go and use our equilibrium equations to solve this problem. If we had an indeterminate beam, right, if we had one more reaction, we would need to use a method. And methods are a little bit more tricky. They take a little bit longer to work out. But we have a determinate beam, so we can just write our equilibrium equations and we can solve this problem. So we have sum of forces in the X direction is equal to 0. So we're looking at any forces acting to the left will be negative and any forces acting to the right will be positive. Then we have sum of forces in the Y direction is equal to 0. So any forces acting in the upwards direction we can say is a positive, and any forces acting down, negative. And then we have sum of moments about a point is equal to 0. So we have a point here. Any forces acting in the anti-clockwise direction we'll say is a positive, and any moments acting in the clockwise direction we'll say is a negative. So these are our equilibrium equations. So let's write our equations. So if we look at our beam, we have sum of forces in the X direction. We're going to look at sum of forces in the X direction. We have our reaction that's in the positive, so we can write that. So let's say AX, and we don't have any other forces. So AX is going to be equal to 0. In the Y direction, we have our reaction in the positive direction. We have a positive AY, and then we have a negative 15 kilonewtons acting on the beam. So we have minus 15 kilonewtons, and that will be equal to 0. All we do is we move our 15 kilonewtons to the side and we find our AY reaction. And then we have our moment. So this moment is acting at this point, at our point of A, and it'll be going in the anti-clockwise direction, right? So we can write positive MA, and then we have a negative moment acting in this direction around that point. We have a negative moment acting in that direction, and the distance is 3 meters. So we have minus 15 kilonewtons times 3 meters, and that will be equal to 0. So our moment at A around point A is equal to 45 kilonewton meters. So now we've found our reactions, our three reactions. We can redraw our beam, and then we have a point load 15 kilonewtons. This distance is 3 meters. This distance is 2 meters. And then we have our reactions. So our MA is equal to 45 kilonewton meters. Our AY is equal to 15 kilonewtons. Our AX is equal to 0. So now we have our cantilever beam with all our reactions. So now we can draw our shear and moment diagrams. So let's project our beam. We have our shear force diagram and we have our bending moment diagram. All right, so our shear force, we have a positive 15 kilonewtons going up. So this will be 15 kilonewtons. And we don't have any other forces until we get to this negative 15, right? So it's just going to be straight line till we get to this 3 meter point, and it's going to go down. And then it will continue, and we won't have any shear value here. And then we have our bending moment diagram. So we have our positive shear force acting here. So our bending moment must be in the positive direction. It needs to increase. So what we can see is if, say, for example, we made a cut here, we cut this beam section here, and we analyze just this section, we would have a beam like this, and there's no forces acting here at all. So the shear will be 0, and the moment will be 0, right? So because this is going in the positive direction, if we start from our 0 point and we go in the positive direction, we actually end up with a positive bending moment when we get to our 5 meter point. But we don't have that. We need to consider this 45 kilonewton meters, right? So this 45 kilonewton meters will go down. It'll be 45 kilonewton meters here, and then it will increase linearly, right, until it gets to the 0 point, and we have a 0 bending moment throughout the rest of the section. So this will be a negative 45 kilonewton meters, and we have a positive or an increase in our bending moment till we reach 0. Okay, so this will be our final bending moment and shear diagrams.